Okay, so since last time we had talked about almost complex structures in general, I thought it was worth like having some discussion of an interesting example. So this is going to start with something that seems a little off topic, but I think it's actually interesting and it will turn out to be relevant. So it's a sort of famous theorem that if you have Rn and you give it the structure of an R algebra, so it has an associative R structure. Oh, I totally lied. I don't know why I wrote that. I should have written division here, right? There are lots and lots of, weird non-semi-simple algebra structures on finite dimensional R vector spaces. But division algebras, there are very, very few. Division algebra means that every non-zero element is invertible. And the only ways you can do that are R itself, C, and then the quaternions. And there's this kind of funny series of, as you go to the powers of 2, you get successively more interesting but worse algebraic structures. So at dimension 2, you get C, which is a perfectly good field. You know there aren't any field extensions beyond that, but at 4, you get the quaternions. And then at dimension 8, you get this guy, the octonions, which is not an associative algebra. You can check that there's no associative algebra of that dimension, but it has this property of being alternative, which is that the associative property holds if x equals y or y equals z, but not necessarily otherwise. So this is a really interesting object. It's responsible for the existence of a bunch of exceptional Lie groups and Lie algebras, like pretty much all of them can be described using the octonions. But I want to sort of talk more about our actual interest, which is almost complex structures. So every one of these has a unique inner product. On C, it's sort of the obvious one that's related to length as complex numbers, which allows us to define an imaginary subspace as the stuff that's perpendicular to 1. So in C, this is just the span of I over R. In the quaternions, this is the span of I, J, and K. And similarly in the octonions, you can write the octonions as generated by I, J, and L. And if you, anyways, you have 7 imaginary things instead of 3, and you have some complicated rule for how they multiply. All right, so having this imaginary subspace and an inner product means there's a unit sphere in the imaginary subspace. When I started with dimension n, I get a sphere of dimension n minus 2. So this is, the empty set inside R, S0, given by I and minus I in C, and then higher dimensional spheres, S2 and S6, and the quaternions and the octonions. So this is sort of a weird thing, but there's actually a really interesting geometric structure that sits on this guy. So this is a submanifold, since it's defined by, well, it's defined by sort of reasonable equations. So and you can check that the tangent space can be identified with the perp to the span of 1 and the point itself in the complex numbers, quaternions, octonions, etc. So in the complex numbers, well, this would just be trivial because the tangent space to C at I or minus I is spanned by 1 and I or minus I. But in the quaternions, you would get something that's 2-dimensional, and in the octonions, something 6-dimensional. And this actually allows us to define an almost complex structure on the sphere, which is at each point, you think of the tangent space as a subspace of the quaternions or the octonions, and you multiply by that element. So the key thing you need to check is that if you have a unit imaginary quaternion or octonion, then its square is -1. It's obvious for unit imaginary is I or -I. And essentially the key fact here is any unit imaginary number, and 1 generates a copy of C inside either the quaternions or the octonians. And so you're doing a calculation in that copy of C, which obviously you get -1. All right, cool. And it's a little bit of algebra, but not very hard to check that multiplication by that element preserves the tangent space. And I'm using here both that it's imaginary and that it's unit one. Josh, yeah.
So are we looking at the unit sphere inside of the imaginary subspace or inside the whole thing?
Yeah, inside the imaginary. So it's useful, even though it's a bit silly, to think about the example of C. So here's C, here's the real axis, here's I times the real axis. So the imaginary subspace is this guy. And then the unit sphere is going to be the points I and -I.
And then we're looking at its tangent space?
Yeah, so of course this example is kind of silly because it's a submanifold, but it's 2 points. So its tangent space is trivial. If we were in the quaternions, right, the imaginary subspace is 3-dimensional. It has I, J, and K as unit vectors. And I'm thinking about the usual unit sphere inside here, right? Mm-hmm. So this is all happening in the space of imaginary quaternions. And so the tangent space at any given point, I can think of as a subspace of the quaternion. So if this point is U, the tangent space TU S2 is I look at the span of 1 and U over the real numbers. As I say, that's actually a copy of C. And I look at the perp to that. And that's a 2-dimensional subspace. And if you kind of think everything through, I mean, this is basically just the observation that if you look at the unit sphere in Rn, the tangent space to a point is the perp to that point thought of as a vector. And then it's a little bit of algebra to see that because I'm thinking about quaternions, multiplication by that quaternion actually preserves that tangent space. If you are familiar with how quaternions correspond to rotations, right? You can think of rotations as corresponding to imaginary quaternions, and it's exactly that you're doing rotation around that axis, right? And the fact that it's a unit quaternion is exactly what tells you it's going to be exactly a quarter of the way round, so that when you square it, you get -1. All right. So because this is kind of an example, I'm not going to go like deep into the algebra. That's something I'm happy to talk about later, or that you can work out on your own. But I promise it does work out. And it works out also in the octonions. Obviously, the algebra there is much harder, but like actually the proof is literally exactly the same. And so you get this almost complex structure on S2 from the quaternions and on S6 from the octonions. Now, for S0, of course, coming from C, well, if you have a bunch of points, they all have an almost complex structure, which is the tangent space is the zero vector space. And so like any map, there's only one map of that to itself, and its square is multiplication by -1. So that's an almost complex structure in the stupidest way possible. On S2, so it's a homework question to show that you get CP1 with its obvious complex structure as CP1. And for the octonions, well, we get some almost complex structure on S6. What is it? There's just something, right? I mention this because we're going to start talking about, well, why do I say almost? Because there's this stronger notion of complex structures. And this is a good example of a complex structure that comes up in nature where it's not obvious, an almost complex structure that's not obviously complex. And at least until you do a bit of work, it's not obviously not complex. All right, any questions? I know I went through this fast. Let me, if you got a little lost, let me just emphasize there's this kind of crazy algebraic structure, the octonions, and it gives us, amongst many other things, an interesting almost complex structure on S6. All right, cool. So last time I was kind of vague about what that almost was there for, right? And we sort of said some analogies about, oh, it's kind of like requiring flatness for a Riemannian metric, or requiring this, the two forms closed condition for symplectic forms. But in order to explain really why that almost is there and what it means to be complex, let me kind of step back a little bit and sort of start trying to wrap our minds around what it means to do all this differential geometry stuff, thinking in the complex world, because I know it's all a little strange. So let's talk about how to complexify some of the basic notions we've been talking about. One thing we've talked about a lot is tangent vectors. Well, tangent vectors come from, you have a map of R into your manifold, and you think about what happens when you sort of move an infinitesimal amount along R, you get a velocity vector, right? And that's at least one way of defining tangent vectors. So what would a complex tangent vector be? It would be whatever it is that comes from a map of C into your manifold instead of a map of R. Well, if you have a map of C into your manifold, you could differentiate it, but you don't get one tangent vector, you get two tangent vectors, right? You get you can think of the tangent space to C as C itself. And so one goes to a tangent vector, which is what happens when you travel along the real axis, and I goes to a tangent vector, which is what happens when you travel along the imaginary axis. And usually we end up writing this. This is a little awkward if you really take kind of doing linear algebra in a coordinate-free way seriously. We write this as the tangent vector along the real direction plus I times the tangent vector along the imaginary direction. So what sort of thing is this? It's an element of the tangent space which is complexified. So it's an element of the complexified tangent space. Or this tangent space, that's a real vector space, and we tensor with C. I'll just mention, when you have a map of C into, well, you're probably only used to a map from C to itself, or maybe a map from C to Cn. There are these Cauchy-Riemann equations that measure whether that map is holomorphic. And that's a statement about the relationship between the tangent vector along the real axis and along the complex axis, the imaginary axis. So actually, the Cauchy-Riemann equations can be phrased as, I have my tangent vector at a given point for my complex map, and well, I have to be mapping into something with an almost complex structure, for example, C itself. When I act by the almost complex structure, that should be the same as doing multiplication by I and C. All right. So if you go back and think about what the Cauchy-Riemann equations for a map from C to itself say, that's exactly what's happening. That when you take that tangent vector that's complexified, you hit it with the map on the tangent space. So the confusing thing here is, if I have C itself, and I take its tangent space at some point, and then I complexify that, well, that's not C, that's two copies of C. So there are two different maps on this guy, one induced by I and one induced by the almost complex structure on C, which of course is multiplication by I, but here. So it's important to keep in mind that when you complexify the tangent bundle of a manifold that's already almost complex, you get two different maps. One which is multiplication by I in the complex numbers, and one of which is induced by the almost complex structure on your manifold. And the Cauchy-Riemann equations say that those are the same. All right. Cool. So in general, whenever we have a complexified tangent vector, so this is an element of TPM tensor over R with C, then I can look at the induced linear map by the action of an almost complex structure J. And of course, because it's squares minus 1, well, the only eigenvalues it can have are I and minus I. And my tangent space becomes the sum, complexified tangent space, becomes the sum of the I eigenspaces and the minus I eigenspaces. All right. And we call things in the I eigenspace holomorphic, or J holomorphic, because they sort of correspond to the tangent to a holomorphic map under Cauchy-Riemann, and ones with eigenvalue minus I, anti-holomorphic, because they correspond to an anti-holomorphic map under Cauchy-Riemann. And as I was just saying, by some basic linear algebra, our complexified tangent bundle breaks up into two sub-vector bundles corresponding to the I and the minus I eigenspaces of J. And so this is why you complexify. On the real tangent space, there's no decomposition like this, right? So if I just have a normal old tangent vector to my manifold, I can't ask whether it's holomorphic or anti-holomorphic. That doesn't make any sense because it can't be an eigenvector for I or minus I. So this is a property that a complexified tangent vector, which is really a pair of tangent vectors, has. And it's a question about how the almost complex structure acts on the span of those two tangent vectors, whether it preserves it and sends them one to the other in the right way. So if I have, here's V1 and V2, then if J, oh, no, that's terrible. We all know that V1 is here and V2 is here. So if J acts by rotation quarter of a way around, preserves this span, sends J to V1 to V2 and V2 to minus V1, then that's holomorphic because J is acting like I. And on the other hand, if I have V1 and V2 down here, oh no, sorry. If I have these guys and instead J acts like minus I, so it sends V1 to minus V2 and V2 to V1, then that's anti-holomorphic. And if you're not used to this term anti-holomorphic, it means think about something that involves I and replace I by minus I. So take whatever you did and stick a conjugate in. All right.
I have a question.
Mm-hmm.
So in the last lecture, we defined J as acting on just the tangent bundle of M.
Mm-hmm.
But now, so does that J from last lecture, is that inducing a map on the tensor product, with the complex numbers, or are we defining a new map here, a new J?
Sorry, I do mean take the one from before and tensor it with C. So, if you're not sort of used to thinking about tensor product as a functor, what that means is pick a basis of your original R vector space. The action of J has some matrix with respect to that basis.
Mm-hmm.
Now think of the same vectors as a C basis of the tensor product and use the same matrix to define a linear map on that C vector space.
Okay, thanks.
That's what, yeah. So I should emphasize here that if J from Tm to Tm is almost complex structure, then there exists an induced map J, which I'll just also call J on the complexification. And somehow the key thing here is over the real numbers, a linear map whose square is -1 cannot have any real eigenvalues, right? Because its minimal polynomial is x² + 1, and that has no real roots. So there's no interesting eigenspace decomposition for the real endomorphism, but after a tensor with the complex numbers, well, every linear map over the complex numbers has an eigenvector. And in fact, because the minimal polynomial is x² + 1, you have to be the sum of the I and minus I eigenspaces. And if you sort of look at this picture, basically what's happening here is anytime I have a plane that's preserved by J, so over R, the smallest dimensional subspace I could have preserved by J is 2-dimensional. I can't have 1-dimensional because there are no eigenvectors. Then you can look at this picture and figure out how out of that plane you can get a sort of 1-dimensional space of holomorphic tangent vectors and a 1-dimensional space of anti-holomorphic tangent vectors. All right, cool. So we can do this pointwise on every tangent space, and we get a decomposition of this complexified tangent bundle into 2 subbundles. And actually, both of these are isomorphic to the original tangent bundle. Because if I start with any usual tangent vector, what I can do is if I take V minus I times JV, that's always holomorphic. And if I take J plus IJV, that's always anti-holomorphic. And I and JV is, sorry, V and JV are always linearly independent because there are no eigenvectors. And it's sort of easy to get confused about this. T10 and T01, the holomorphic tangent vectors and the anti-holomorphic tangent vectors, those are subbundles. They're preserved by the complex numbers. And what is it to the tangent bundle with I acting as either the complex structure J on the holomorphic ones or minus J on the anti-holomorphic ones. And this is sort of a standard thing that happens all the time in field extensions, that you start with some structure, in this case, the real tangent space with this almost complex structure acting on it. You complexify it, and then if you forget back down to real vector bundles, you get some sum over the Galois group of your original structure, and then all the ways you could twist it by the Galois group. So in this case, you get back the original tangent space with the original almost complex structure, and then sort of a twist of it by the non-trivial element of the Galois group, which is the almost complex structure minus J. There's also a sort of a dual thing we should note, which is there are also one forms. The obvious way to get a one form is to have a function to R and to take its differential, which eats a tangent vector and spits out the directional derivative of the function with respect to that tangent vector. But if we have a map not to R but to C, well, again, we get sort of a double thing, right? We get not a section of the cotangent bundle, but of the complexified cotangent bundle. Basically, if I have a function that goes into C, its directional derivative is C valued. And so I have one form that picks up its real part and one form that picks up its imaginary part. All right, and basically dualizing everything we did on the tangent space, we also get a decomposition of the cotangent bundle into a. So I really want to say holomorphic and anti-holomorphic because that's what I said for vectors. And that's originally what I wrote in my notes. And then I sort of realized when I got to the end, shit, holomorphic one form means something else. So I shouldn't use that here. And that's why Canis de Silva didn't say holomorphic here. So she says complex linear and complex antilinear. But these are the duals of the holomorphic tangent vectors and the anti-holomorphic tangent vectors. And I'll get to this in a moment. The kind of key point here is, like, why is it that holomorphic one form means something else? It's because this is a property that's only about kind of what's happening in each individual tangent space. In each individual tangent space, when you multiply by the almost complex structure, do you multiply by I or by minus I? But it's nothing about how things vary. So at the moment, the sort of way you can relate this to kind of usual notions of holomorphicity is if I have a function to C, then that's holomorphic if and only if the corresponding differential lies in this 1,0 part of the cotangent bundle for every point. And again, this is like just taking the Cauchy-Riemann equations and kind of translating them into this language. All right, any questions? I know this is weird stuff. I think we'll get a little more comfortable with them as we work with these notions of holomorphic and anti-holomorphic tangent vectors, 1, 0, and 0, 1 form. So people don't often actually say complex linear and complex antilinear. They'll just say a 1, 0 form and a 0, 1 form, and sort of with everyone knowing that that means you're in one eigenspace or the other eigenspace for the action of J. Yeah, Hugh.
Hey, Ben, sorry, I got kind of confused about what you said about holomorphic K-form being already taken. Were you then going on to explain what it means, or were you explaining? I'm just confused about what you were trying to get at.
Oh, sorry. So I am going to explain later in the class. The sort of the issue here is, so we'll get to this later. When we have a function, that function, when I take d of that, I can write that as the sum of two different contributions, which are usually written partial f and partial bar f, where this is a 1, 0 form, and this is a 0, 1 form. And f is holomorphic if and only if d bar of f is equal to 0. So this is which is the same as saying that df is a 1, 0 form, right? That it's equal to partial f. So in general, people say that a K form is holomorphic if usually this means that del bar of C is equal to 0. So there's sort of, it has trivial derivatives in kind of the anti-holomorphic directions. And that's just like, that involves the derivatives of the values. So like, this is going to be easier to explain when we've talked about things more in coordinates. But that's what's going on there. That being a 1, 0 form tells you nothing about how the 1 form varies as the point changes. It's a purely tensorial property. It's just a statement about what kind of covector are you at each point, whereas being holomorphic is a property that involves taking differentials.
Okay, yeah, I think that's clear. Yeah, I mean, it's just sort of already taken, but it's taken for a related notion that we're going to come to later.
Yes,
So
yes. And yeah, in part I mentioned that because I was preparing the notes and I wrote holomorphic and anti-holomorphic 1 form there, and like those words mean something else. And then I realized my mistake and was like, oh shit, I shouldn't do that. So I think pretty much everyone says 1, 0 form and 0, 1 form. Okay. And let me just say there's sort of a general notion of holomorphic maps between almost complex manifolds, which is just maps whose differentials always commute with J. And you can check that this notion of holomorphic up here is the same as this one. So this is kind of a more general repackaging of what the Cauchy-Riemann equations say. Hugh, do you still have a question?
no, sorry, I'll take my hand down.
Okay.
I have a question. I think it's pretty stupid, probably.
Okay, I welcome stupid questions.
So is every 1 form either complex linear or antilinear?
No, it's a sum of
Okay.
one that's linear
Okay.
and one that's complex antilinear, right?
Thanks.
It's an eigenspace decomposition. So yeah, it's a direct sum. So everything is a sum of these two things in a unique way. All right, well, let's upgrade this to K forms. So just to have some notation at hand, right? K-forms are sections of the kth wedge power of the tangent, the cotangent bundle. And I'm adding a C here to mean the kth wedge power of the complexified cotangent bundle. And I'll just mention, right, it doesn't matter whether you take wedge power first and then complexify, or complexify and then take wedge power. But of course, if you have wedge power over R, if you have, you need to take wedge power over C. All right, whenever we have a vector space, and my direct sums ended up a bit tilted, so let me make that a little more carefully. And it's a direct sum of, sorry, that actually was supposed to be a tensor product, sorry. Whenever you take a vector space and you break it up as a sum of two things, and you take its wedge power, then you get a nice decomposition of the wedge product, which is, you can think about wedges where you take L things from one summand and M things from the other summand. And I just want to mention, because this is a wedge power and you have this anti-symmetrization, I'm not telling you which L things come from one guy and which M things come from the other guy. They're kind of all mixed up, but I can say that L of them came from the 1, 0 space, M of them came from the 0, 1 space. And unsurprisingly, we call the results LM forms. Right, so this guy is usually called TLM. And sections of it are written as omega LM and called LM forms. So again, this is a purely linear algebraic notion, or tensorial, right? It's just, I look at the value at one point and I say, okay, being an LM form means I will only get a non-zero answer if I put in L holomorphic tangent vectors and M anti-holomorphic tangent vectors. And if I put in any other number of holomorphic tangent vectors and anti-holomorphic tangent vectors, I will get 0. All right, and of course, attached to this direct sum decomposition, I have a projection. All right, any questions? So this is something that I can take any complexified K form on my manifold, which is, you'll remember, kind of two usual K forms, a usual K form and then I times a usual K form. And then I can start looking at, well, what happens if I take this K form and I put in, if I only pay attention to what happens when I put in L holomorphic tangent vectors and M anti-holomorphic tangent vectors. And there's sort of this projection down to an LM form, which is sort of the part of the form that only picks up those kind of inputs. Whoops. In particular, so I had talked about how this happens with functions, but in general, you can look at exterior derivative of, let's say, an LM form, and then look at the projection of that to the different types. And in particular, we have these operators del, which is if you increase the number of holomorphic tangent vectors, and del bar, where you increase the number of anti-holomorphic tangent vectors. Or, so one of those is projecting to L plus 1M, one of them is projecting to MLM plus 1. And one thing I want to mention, I'm not claiming that those are the only one of these pieces that I get a non-zero projection to. So there are other pieces in that direct sum, and I have to at least consider the possibility that the exterior derivative has non-zero projection to them. And spoiler alert, that's going to be the difference between almost complex and complex manifolds. So one of the ways of saying this difference between almost complex and complex manifolds is that on complex manifolds, the exterior derivative is only del and del bar, and on almost complex manifold, which isn't complex, there will be other components that show up somewhere. All right, so yeah, let me pause for questions. I know this is like, believe me, it took me like a long time to kind of wrap my head around these LM forms. They're strange beasts, but we'll get down to talking about them more in coordinates, and I think they'll be clearer then. And oh, okay, so I think Justin couldn't make it today, but I'll just pause for a moment and let people think, sip my tea, and if people have questions, they can ask. And I will go back up to what we were talking about before.
All right, I have a question. When you have if you have an LM form and you take exterior D of it, the total degree has to go up by 1, right? So what other components could you have? Just anything where the either L goes up by 1 or M goes up by 1.
Okay. So we'll get to this later. So maybe this is spoiling my spoiler or something. But if you think about the formula for exterior derivative, right? So the exterior derivative of a form applied to k plus 1 things is equal to, should actually look up this formula, because I'm going to screw it up if I try to do it from memory. It's hard to get all the signs right. Let me actually pause for a moment, look up this formula.
I remember it for 1 forms, but then, yeah.
Yeah, right, it gets a little bit complicated. So you take the sum minus 1 to the I, derivative with respect to VI of my form applied to V0. I skip VI up to VK. Okay, so what's happening here? I'm putting some number of vector fields into this derivative. I'm throwing out one of them, and then I'm evaluating. So this term, you're right? If I put in here L prime holomorphic things and M prime anti-holomorphic things, well, if I pulled out a holomorphic thing, I'll either have L prime minus 1 M prime or L prime M prime minus 1 things going in here. So this part, I can only change one of the indices by 1.
Right, right.
But then there's another part of the formula, which is sum minus 1 to the I plus j, and I can't do this from memory. Probably if I really thought hard about the Cauchy sign rule, I could get this right. I take the Lie bracket of these two. So I have to be using an actual vector field here for this to make sense, but I take the Lie bracket of these vector fields and I take V0 and I exclude both of these guys. And so exactly the problem here is that if I take the bracket of two holomorphic vector fields, it might not be holomorphic. So if there's an anti-holomorphic component to this, I could be getting things off by 2. So I sort of could be putting in here L minus 2.
It'd be like you drop 2 holomorphic spots, but then you gain 1 anti-holomorphic.
Yeah, something with a non-trivial anti-holomorphic component.
Right, I see.
So the worst that can happen is one of them goes up by 2 and one of them goes down by 1, but that's a real possibility.
Got it. Thanks.
Right. Any other questions? Okay, I'm feeling okay, so I guess I'll get back to things. So let's actually talk about what complex manifolds are. So you'll see kind of different versions of this. You know, if there's anything out there in the world that has to be a complex manifold, it's Cn itself, right? Obviously, there's no good definition of complex manifold that doesn't include Cn. So the tangent space to Cn is, of course, Cn again, and multiplication by I is a real linear map whose square is -1, so it defines a complex structure. A little more explicitly, we can pick complex coordinates Z1 up through Zn. We can break those up into their real and imaginary parts, xi and yi. And what's going to happen here is that j of ddxi is ddy, and j of ddy is minus ddxi, writing out explicitly what it means to multiply by I on the tangent space. And I'll just note here, there's a compatible triple for this guy, which we talked about last time, where we take the obvious metric. I'm writing this in kind of differential geometry style of dxi squared, dyi squared, but it's the obvious metric, the usual inner product on Cn. And then the symplectic form, that's dxi wedge dyi. And I shouldn't have made those curly because I don't mean del. I mean the usual exterior derivative of these guys, forgetting about any complex funny business. And you can check that this is a compatible triple of a complex structure, a metric, and a symplectic form. All right. Now we call an almost complex manifold complex if every point has a neighborhood which is biholomorphic to an open subset of Cn. So I'll just remind you, when I say biholomorphic, I think this is sort of the standard word. It's a map which is bijective, holomorphic, and its inverse is holomorphic. So another way to say this is a diffeomorphism, an isomorphism on tangent spaces, which is holomorphic, commutes with the action of J. Right, so from the perspective of the almost complex structure, your guy looks like it's a subset of C. Now, if you look in Canis de Silva, you'll see she writes this a little bit differently, because she basically writes the definition of a complex manifold you would use if you didn't know what an almost complex structure was. Right? So in that case, what you would do is you would say, I have an atlas on my manifold such that everything in the atlas is isomorphic to an open subset of Cn. But if I don't already know what an almost complex structure is, I can't ask that each of those maps is holomorphic itself. I instead have to throw in this condition of such that when I do the transition map between any pair of them, the composition is holomorphic or biholomorphic, right? So if I were asking for a usual manifold structure, I would just want this to be a diffeomorphism. But because I also want an induced complex structure or almost complex structure, it has to be biholomorphic. So to check the equivalence of these, you know, the important point is if we have this kind of complex atlas, then we can construct an almost complex structure in the sense that we discussed on the original manifold, basically by just transferring it from the open subset of Cn to Ui, and this biholomorphic condition is exactly what you need to get the same answer on overlaps. And Canis de Silva says a little bit more about this, and the point is somehow like there are a few different ways you could write down exactly what it means to be a holomorphic map. And again, if you hadn't already discussed the notion of a complex structure, you would write down the Cauchy-Riemann equations in some other way, and then you would have to explain why that's the same as the definition I gave about having the differential, the derivative commute with the almost complex structure. All right, any questions? So, you know, this is kind of stronger than the, you know, kind of usual, what do I want to say? Yeah, maybe I'll get to this later, but you'll note here, right, this is a very differently flavored definition from, say, being a symplectic manifold, right? A symplectic manifold is something where, you know, I have a two form and I have some conditions on, you know, derivatives, basically that it's closed. Whereas here I'm saying, well, it looks like a model structure that I already have. So it's not kind of an intrinsic definition, it's a definition that comes from comparing with something else. And we now know that the symplectic form also can be defined that way using Darboux theorem to say it looks like the cotangent bundle of Rn, but there was some work in matching those up. All right, so I think it will be clearer if we kind of write out how these 1, 0, and 0, 1 forms work on Cn, which for a complex manifold is the same as doing it locally anywhere. Locally on a complex manifold, there's some neighborhood where there are coordinates that look like the coordinates on Cn, and I can use them here. So I, of course, have my complex coordinates I defined before, and I have their complex conjugates. And I can take their differential as before, and I mean, essentially by definition, Zi is a holomorphic map. So its differential is a 1, 0 form. On the other hand, the Zi conjugate is an anti-holomorphic map. Its differential is a 0, 1 form. And the thing I want to kind of emphasize here, right, is that I can take any functions I want with no requirement of being holomorphic, any smooth functions, and take a linear combination of dz's with respect to those, and I get 1, 0 forms. So that's kind of how this differs from being a holomorphic one form. A holomorphic one form would be, I would have to take my bj's to be holomorphic themselves and then multiply them by these basic 1, 0 forms dzi. All right, similarly, I can write every 1, 0 form as some function like that times dzi bar. And of course, it's convenient to have dual vector fields. You'll note here there are some funny factors. There are these factors of a half, and there's a minus and a plus here. And that's just, I'm taking the dual basis to the zi's and zi bars. So there's a transpose that shows up somewhere. And I get this half. Yeah, transpose inverse, I should say. And I get this half and the changed signs. And using this kind of new basis, it's a little weird, right? It's like I'm changing basis on R2n, but it's not to a basis of R2n. I'm sort of using this complex direction in a funny way. But I can still write the differential of any function as df ddzi times dzi df dzi bar dzi bar. Right, this is still kind of a valid equation using these complex vector fields and complex one forms. This equation makes sense for any function, real or complex valued. So I can put in a real valued function. Now, each of these terms separately is going to be complex valued. I'm going to need to like complexify to get this decomposition. But it makes perfect sense for a real valued function or for a complex valued one. All right, and I guess I didn't write this before, so good thing I'm writing it now. This gives us an explicit formula for del of f and del bar of f. Those are by definition that I take d of f and I project to the 1, 0 forms and the 0, 1 forms. And well, again, it doesn't matter all what this derivative is. It can be any kind of crazy function. I know this guy is a 1, 0 form because it has dzi here. And I know that this is a 0, 1 form because it has dzi bar. All right, so being holomorphic in the usual sense of a function is exactly that del bar of f is 0. More generally, if I take any LM form, I can write that as a sum of some functions times taking the wedge of L dzis and M dzi bars. So, the way to think about what an LM form is, it's something that when I expand it out in these coordinates, has L appearances of dzi and M appearances of dzi bar. And again, somehow this wedge product doesn't have an intrinsic order. I mean, if I swap order, I swap -1, but I can look and I can say, okay, how many of the terms here are dzi? How many of the terms here are dzi bar? And that tells me what an LM form is. So on C, I can then compute the exterior derivative of this guy, right? All I have to do is take d of these coefficient functions b and wedge that with dza and dz bar b. These guys are already closed because their exterior derivative is 0. I can then use this way of splitting functions, the differential of function as del plus del bar, and I get that dc is del c plus del bar c. Whew, all right. So this tells us that if we have a complex manifold, then it's correct that d is del plus del bar. And if you think back to my answer to Matthew's question, how would I justify that in the terms I was using there for kind of formulas for the exterior derivative? Well, the point is now I can figure out what the exterior derivative of C is by evaluating it on the vector fields of the form ddzi some number of partial zi's and partial zi bars. And when I do that, that term that involved commutator, which caused me the problem before, is always 0. If I take the bracket of any two of these vector fields, they commute, and the bracket is 0. So that term that would have potentially caused me trouble goes away. Great. And you know, if you, yeah, we'll talk about this more later. So if we have a complex manifold, then the exterior derivative is exactly just del plus del bar. There's no other funny business going on. And in fact, the converse is true. If the exterior derivative is equal to del plus del bar on all k forms for all k, then the manifold is actually complex. So this is kind of a more intrinsic characterization of, well, when is an almost complex manifold complex? All right. Any questions? Let me go back to a little bit of this more explicit linear algebra stuff. So this is sort of, at least to my mind, a kind of helpful way of thinking about these LM forms. Okay, so I wanted to at least explain a little bit about why this statement is true, that partial is equal to del plus del bar implies that the manifold is complex. Now, I think it's at least plausible from that discussion we had before that actually you only need to check this on 0-1 forms or 1-0 forms, either way. That somehow kind of all of the action, right, was in this term in the derivative, in the exterior derivative that involved taking the bracket of the vector fields. And you don't see that when you take the exterior derivative of a function, because a 1 form never eats 2 vector fields. But as soon as you're taking the exterior derivative of a 1 form, you're getting a 2 form, and that problem will show up. So I'm mostly kind of writing out things I did before, but it's a little clearer in this case. If I have a 1-0 form, I take its exterior derivative. Well, I can break that up into a 0-2 form, a 1-1 form, and a 2-0 form. The 0-2 form is del bar. The 1-1 form is del. And the 2-0 form is the obstruction to exterior derivative being del plus del bar. Right. So what you can check here is, so by definition, this projection to the 2-0 form is 0 if I put in 2 vector fields and one of them is anti-holomorphic. So I'm kind of only interested in what happens when it eats 2 holomorphic vector fields. And by that argument I gave above, right, if I take the exterior derivative and I evaluate it on 2 vector fields, so that formula up above simplifies quite a bit. I get that d c x1 x2, right? Hopefully I'll get these signs right, is the Lie derivative with respect to x1 of c eating x2 minus the Lie derivative of, with respect to x2 of c eating x1. But if c is a 0-1 form and x2 and x1 are holomorphic vector fields, these guys are both 0 automatically. Right? We'd already discussed that sort of this portion of the exterior derivative is never going to cause you a problem in this respect. And then there's finally just c eating the Lie bracket of these two vector fields. Okay. So exactly where I could get something non-zero here is if I take the bracket of two holomorphic vector fields and I get something that's not holomorphic, that has a non-zero anti-holomorphic component, and thus is going to have non-zero evaluation against some 0, 1 form. All right, and that's exactly what I sort of say here. If you have two holomorphic vector fields, if that Lie bracket isn't holomorphic, it's going to have non-zero pairing against some Xi, and I can find an example of Xi where the exterior derivative is not del plus del bar.
Can you say again why those terms are zero, those Lie bracket terms?
Oh yeah, because Xi is a 0, 1 form, and x1 and x2 have to be holomorphic, have to be in sections of T10, right? So essentially the definition of a 0, 1 form that it has trivial evaluation against every 1, 0 vector field, every holomorphic vector field. So by the definition of either a 0, 1 form or holomorphic vector field, this guy that I'm differentiating is already 0. So I'm certainly not going to get something non-zero by differentiating.
Thanks.
Mm-hmm. All right, so we've kind of reduced to the question of, can I take a holomorphic vector field and another holomorphic vector field, take their Lie bracket, and get something that isn't holomorphic? So, well, I just say, okay, well, every holomorphic vector field is the form of some real vector field u minus iju, and any other one is of the form of some real vector field v minus ijv. And I just take the Lie bracket of those, and I see what expression I get. So I get this expression here. Sorry, here's, whoop, sorry about that. Here's the real part. Here's the imaginary part. Is this guy holomorphic? Well, I get some expression which has to vanish in order for that guy to be holomorphic. And we get what's called the Nijenhuis tensor. So from just this kind of algebra, we see this Nijenhuis tensor, that's the obstruction to D is equal to partial del plus del bar. So this is sort of, yeah, it's kind of dualizing the operation of taking a 0, 1 form and looking at the 2, 0 component of its exterior derivative. It's kind of the dual operation on vectors of, well, when I evaluate that 2, 0 part against two vectors, like, do I get something non-zero? Now you note here, this is called a tensor. Tensor, I keep using this word. Let me just remind you that sort of, it means that it's something that only depends on the value of the vector field at the point P and not on any derivatives or anything like that. And we call an almost complex structure integrable if this Nijenhuis tensor is 0. So, which is the same as saying if the exterior derivative is del plus del bar. Okay. Whew, any questions? So exactly what this Nijenhuis tensor is doing is it's picking up the failure of the Lie bracket of holomorphic vector fields to be holomorphic, to again be holomorphic. All right, and then theorem of Newlander and Nuremberg. Nuremberg. So this is awful. There's the 9-house tensor, which is the kind of key object in the Newlander-Nuremberg theorem. But, you know, what can you do? You don't have to decide who that n is in honor of. It can be for everyone. A manifold is complex. A manifold with an almost complex structure is actually a complex manifold if and only if it's integrable. So this is kind of the analog of the closed condition for symplectic forms or the flat condition for Riemannian metrics, right? So we could have defined symplectic manifolds as like manifolds with a symplectic atlas, right? You could define what a symplectomorphism between two open sets of R2 is. A symplectic if it has an atlas by charts inside R2n such that the transition maps are symplectomorphisms in the standard symplectic structure. And the Darboux theorem tells you, oh, well, you have an atlas like that as long as your 2 form has trivial exterior derivative. And similarly, like you could define a flat Riemannian metric as something which has neighborhoods, which are an atlas which is isometric to Rn with its usual flat metric, such that the transition maps are isometries. And then you could say, oh, well, actually, there's this intrinsic characterization. The Riemann curvature tensor has to vanish. So this is kind of a complex analog of the Riemann curvature tensor, or the exterior derivative of the symplectic form. You know, when I was sort of reading around this, I was reminded Nuremberg is, you know, one of the most prominent Canadian mathematicians of the 20th century. He's one of 2 Canadians who's won the Abel Prize. And Newlander was his student and apparently was never heard from again. I could find literally nothing else about him. But he got his PhD with Nuremberg in, I think, 1957 and just disappeared off the face of the earth. Funny how these things go sometimes, but he's achieved immortality in getting his name attached to this theorem. All right, any questions? By the way, you might wonder, you know, we went through a proof of the Darboux theorem. Wasn't that easy, but it wasn't that hard. Didn't require anything like extremely deep or complicated. In particular, it didn't require any hard analysis, which is nice. You know, what I myself had kind of wondered, okay, actually how hard it is to prove this theorem. Canis de Silva kind of tells us nothing about it. I would say that this is a bit more complicated. So more complicated than Darboux. So sort of the key thing actually is, you know, what you need to prove this theorem is to start with the almost complex structure and around any point find kind of enough holomorphic functions. And if everything is a real analytic, so everything is a limit of a power series, basically, you know, when you sort of write down some chart, your almost complex structure, all of the coefficients of it in the chart are real analytic, their Taylor series converges to them, then this is essentially sort of formal. You can solve for the holomorphic functions you need by just writing down their Taylor series. You just kind of say, okay, like being holomorphic in this almost complex structure is kind of this linear algebra condition on the Taylor series. Oh, I can solve that linear algebra problem. So here's the Taylor series of my holomorphic functions. But if you don't already have that, and you don't want to assume that, then you have to do some actual analysis to change coordinates so that everything becomes real analytic. So use elliptic PDEs to change coordinates so things become analytic. And so the sort of key thing that I would say makes this harder than Darboux theorem is Darboux theorem only required solving an ODE, and I was willing to assume that you knew, the basic idea that you could do that and what it meant to do that. Whereas proving this requires a more complicated theory requires using PDEs, but on the other hand, it's only elliptic PDEs, which is, I think most people would say, the easiest part of the theory of PDEs. So, you win some, you lose some. I looked up some notes that had a proof of it. It wasn't like a long, difficult proof. It was like a page, but it sort of assumed that you were comfortable with the idea of, here's how solutions of elliptic PDEs act. Okay. So I had left us at the start with this mystery of what about this complex structure on S6? And I think I had to wait to this point to bring it back. So I'd introduced you this almost complex structure on S6, and now we know how to check whether it's complex or not, right? So one of the nice things about this 9-house tensor, right, is if something has a complex atlas, you can just write down the damn complex atlas. But if it doesn't, you need to have some obstruction to one existing, some way of showing that there isn't one. And well, now we know what we can do. We can calculate the 9-house tensor and show that it's not zero at some point, and that will prove we're not a complex manifold. And actually, you can check on this S6 in the octonions, the 9-house tensor of two vectors, y and z, which I can think of as octonions at some point x, which I can also think of as an octonion. That's a 2. It doesn't look very 2y, but is 2 times the associator of x, y, and z. So x times y times z minus x times y, z. And since the octonions are not associative, this 9-house tensor is not trivial. So this 9-house tensor is exactly sort of measuring the fact how non-associative the octonions are. So when we do this for the quaternions, because the calculation of the 9-house tensor is the same, but we see that we do get a complex structure because the quaternions are associative. And indeed, as I said, you're supposed to get CP1, which definitely has an honest complex structure on it. Really is a complex manifold. And it's actually a very famous question whether S6 has an integrable complex structure. I suspect that the answer is no, just because if there were one, wouldn't we have found it yet? But we don't know. All right. Any questions? I don't know. In part, why I wanted to bring up S6, I thought this was pretty cool. But you get this abstract 9-house tensor thing, and all it's doing is picking up are the quaternions associative or not? Well, sadly, they're not, or maybe happily they're not. I don't know. It depends on your perspective.
So can I ask, thus far we've studied D is del plus del bar in the case of functions and vector fields?
One forms.
One forms, yes. I assume like this analysis of finding obstructions extends straightforwardly to differential form, to vector fields and higher forms?
So yeah, essentially by let's see, where was that? I know it was off to the side. I guess it's further up. Right. So I did this calculation, and you see it's exactly the same thing showing up.
Okay.
So yeah, if you sort of go through this calculation, you'll see if the exterior derivative of C is not del plus del bar of C, there has to be a k-tuple of vector fields, which are, you know, the kind of right combination of holomorphic and anti-holomorphic, such that either two of them are holomorphic and their Lie bracket isn't holomorphic, or two of them are anti-holomorphic and their Lie bracket isn't anti-holomorphic. Sort of go through this calculation. The only place where sort of the del partial equals del plus del bar could go wrong is if this guy here were the bracket of two holomorphic vector fields and not holomorphic, or the bracket of two anti-holomorphic vector fields and not anti-holomorphic. So yeah, you can prove that. Yeah, that being the partial equals del plus del bar is equivalent to the fact that holomorphic vector fields are closed undertaking bracket, which you can then check as equivalent to this Nine-house tensor being 0.
Okay.
And actually, I'll link there. Denis Roux has like a sort of, you know, pretty sketchy notes about this, but that kind of goes through this argument in more detail. The Candace de Silva kind of skips it. She like this Nine-house tensor shows up in a homework, and I think if you go through that homework and think about it, it's essentially what I've written here in different language, but she's expecting you to go through it as a homework.
Okay, thank you.
Yeah, of course. So, and in general, I think this shows up in Candace de Silva, and it's definitely also in these sort of Roux notes. There are all these kind of different characterizations of being a complex manifold. So following are equivalent, MJ is complex to the exterior derivative is del plus del bar. The exterior derivative is del plus del bar on just 0, 1 forms. It's enough to check it there. T0, 1 closed under bracket. Whoops, I wrote 3 twice. This Nine-house tensor is trivial. You can show that all of these are equivalent. All right, I'm almost out of time, but I just wanted to kind of note one more thing that we'll probably use a little bit later. If we're on a complex manifold, and partial equals del plus del bar, then, well, what happens to the de Rham complex? So we know that if we square the exterior derivative, we get 0. Well, now we can rewrite that as del plus del bar squared, and we end up with the term going into 2 0 forms, del squared into 0, not just 0-2 forms, but going into L plus 2m forms is del squared, into L m plus 2 forms is del bar squared, and then one ends up with this kind of middle term of del bar plus del bar del. So we get that del squared and del bar squared are both equal to 0, and that del bar is minus del bar del. So that part's actually a tiny bit surprising. But if you look at all these forms of different types, you get kind of, instead of just a complex, you get almost a double complex. Up to these issues about sign. Oh, sorry, that should have been del going one way, del bar going the other way. Del going like this, del bar going like this. And since del bar squared is 0, you can compute cohomology just with respect to del bar squared. And that's called Dodot cohomology. So you look at LM forms going to LM plus 1 forms by del bar, you look at the kernel of that, and then you look at the image of L minus 1 forms going to LM forms via del bar, and we get, we take the quotient of the kernel by the image, which is well defined because del bar squared is 0. One particular special case of this is that HL0. So then there's no image. We're just looking at the L0 forms, which are killed by del bar, and that's what holomorphic K form means. So this is the L0 part of the Dolbeault cohomology. And maybe I'll actually just mention here, there's another thing that one could put here. Oops. Another equivalent statement is that del squared and del bar squared is 0. Those are all characterizations of being a complex manifold. All right, so any more questions? So I'll just mention again, you guys should have gotten an email about this essentially immediately before class. I am sorry about forgetting about the office hours last time. And I've scheduled them for tonight. If that works for you guys, I hope it does. And if it doesn't, then send me complaints and I will adjust scheduling.